Hello, for today's video lecture we're going to be talking about free rigid body collisions. So a free rigid body collision is an instance where two non-anchored or movable bodies impact one another, and we're treating at least one of those bodies as a rigid body where rotation can occur. So an example of this kind of impact would be, say we've got a satellite sitting in space, and then some small meteorite comes and impacts this. So after we've got two bodies and both of them kind of freely floating, and the satellite has enough kind of volume to it that we can assume that it's going to rotate after impact. So solving this is going to be a free rigid body collision problem here. All right, so with free rigid body collisions, the impact can end up being very chaotic with both linear and angular velocities for each of the bodies involved before and after the impact. So it's a lot to keep track of. So despite this, with enough information, we should still be able to predict the outcome of an impact given all the information prior to a free rigid body impact. All right, so just as a review, for the types of collisions, we've got elastic collisions, semi-elastic collisions, and inelastic collisions. So we're going to break this down, and we're going to talk about inelastic collisions first because it's going to be the simplest, and then elastic and semi-elastic collisions as a separate issue in this topic. So again, starting with those inelastic impact, this is the simplest rigid body impacts, or inelastic impacts. So because the two bodies stick together in this instance, where we've got two collisions and they kind of wind up sticking together and having one kind of final body at the end, we're just going to have kind of a single final velocity with x and y components, as well as a single angular velocity. So three unknowns after the collision, at least if we're working in 2D here. So for this, we'll need three equations, all of which can be conservation of momentum equations. So an example of this, so say we've got our satellite again, and we've got the micrometeorite that strikes it, and say that the micrometeorite sticks into the satellite and becomes one body afterwards. So because the impact forces are internal to the system, so with both the satellite and the body, so A and B here, are considered part of our system, that is an internal impact, and then that means with no external impact, the momentum is going to be conserved for the body as a whole. So this includes the momentum in the x direction, which is going to have the separate bodies first, so the kind of momentum of A plus the momentum of B equals the combined mass times velocity, so momentum final for the combined system. So we can do that in the x direction, we can do that in the y direction, and then we have the angular momentum. So we've got angular momentum of the two separate bodies initially, and then one final angular momentum at the bottom here. So I don't have a single equation to show for this because it really depends upon the point we're choosing. So if we are going about the center of gravity, it's a little bit simpler. If we are going about some arbitrary point, like the point of impact maybe, that momentum, what we show for momentum is going to be slightly different. So whatever we choose, we need to be consistent. So all angular momentum terms must be taken about the same point. So in this case, I might take it about the center of gravity of the satellite itself in this case. So three equations, three unknowns. There might be some kinematics to relate different terms in here, but that's going to be what we're going to do for inelastic impacts. Next up, we have elastic and semi-elastic impacts. So this is where the two bodies are going to bounce off of one another, and it's not going to be a single body in the end. So in these situations, they don't stick together in 2D. Each of the bodies is going to have its own x and y final velocity as well as its own final angular velocity. So that means we've got, with just two bodies colliding, there are 6 unknowns to solve for. So 6 unknowns means we need 6 equations. So the equations that we end up using in these cases for both elastic and semi-elastic situations are the same. So that's why I've lumped them to get together here. We're going to have the same 6 equations that we're going to end up solving. All right, so let's figure out what those equations might be. Again, because the impact forces are internal to the system, just like we had with the previous inelastic impact, both the linear and angular momentum are conserved for the system as a whole. So this is going to be for everything. The momentum in the x direction is conserved, the momentum in the y direction is conserved, and the angular momentum is going to be conserved. So slightly modified because in the final state they're not stuck together anymore. So we've got velocity a final x, velocity b final x, velocity a final y, b final y, etc. In this whole thing. And the angular momentum in this, again, you need to take it, it can be taken about any point, but we just need to be consistent. So if we're taking it about point A, we need to take the angular momentum about point A for everything in our situation. So conservation of momentum for the system, we've got 3 equations from that alone. So 3 more to go. So next up, we're going to examine the angular momentum of each body individually, and making the same assumptions we did with the surface impacts. Again, impact forces are going to be so large they make other impulse forces or other impulses negligible, and we usually assume that the angular momentum is going to be conserved about the point of impact. And this is for each individual body. So generally that point of impact is not the center of gravity or some fixed axis. So we're going to need to use the arbitrary angular momentum about any point equation. And so it's going to be conserved for point A, or for body A. It's going to be conserved for body B. And this is going to be 2 more equations that we can use. So this is a very similar approach to what we used with the surface impacts. We've just split it up. We've got body A and body B separately in this situation. So 5 equations now, 1 more to go. And our final 6th equation, we're going to use the coefficient of restitution, which is going to be a set number for semielastic collisions, or we just set it equal to 1 if we assume an elastic collision. And this is going to specifically refer to the relative velocity of the 2 bodies in the normal direction. So again, you need to figure out kind of what is the plane of impact. That's your tangential direction. What is perpendicular to that? That's your normal direction. And it's going to be specifically at the point of impact, the velocity of the point of impact on these 2 bodies. So with that, what that's going to look like, so our coefficient of restitution E is going to be negative VA P V normal A for body A at point P final minus the velocity normal of body B at point P final over the same thing basically for the initial conditions. So this is a lot to deal with. There's a lot of subscripts in this piece here. But again, it is the normal velocities. It is body A and body B, initial and final. And this is our final equation for the impact. All right, so with all of this, 6 equations, usually enough math-wise, but one final note is for the elastic and semi-elastic rigid body collision problems, we're going to wind up with velocities at the center of mass G, as well as at that point of impact P. So because of that, we're going to have even more unknowns than we would start with. And to fill in the gap, just like we did with rigid body surface impacts, we need to supplement our equations with kinematic relationships to relate the velocities at point P and point G. So you'll need to work on the rigid body kinematics part, come up with some extra equations relating those velocities, and build even more equations out in your system. All right, so solving these free rigid body impact problems, you're going to start by creating a diagram showing the initial and final states, identify all known and unknown values. You're going to identify the normal and tangential directions. It's going to be important for our elastic and semi-elastic problems. You're going to identify the point of impact P, as well as the center of mass G of your bodies in this case. And then next you're going to write out the equations discussed in the slides, either the 3 equations for inelastic or the 6 equations for semielastic or elastic values. And then add any necessary any equations relating the motion at point P to the motion at point G using kinematics. And then finally solve the equations for unknown values. Again, there's a lot of equations, there's a lot of unknowns. In this case, equation solvers are your friend. All right, that's all I've got for today's video lecture. Thank you for watching, and I hope to see you again.